Now let's talk about subspaces of a vector space. If S is a non-empty subset of a vector space V, then the operations of addition and scalar multiplication on V can certainly be restricted to S. By this we mean we restrict the domains of the two operations. So the restricted addition will map S cross S to V. Not necessarily to S, but to V. When you restrict the domain, it doesn't necessarily affect the codomain or the image of the function. And the restricted scalar multiplication would then map F cross S to V. The problem is we have no guarantee that the restrictions are valid operations on the subset S. In other words, we don't know whether restricting the domains to S also restricts the images to S. For example, if we look at the open first quadrant in the plane R2, so this is the ordered pairs A, B, where A and B are positive, addition is a valid operation on S because when we add two vectors in S in the open quadrant, we get another vector in the open quadrant. But scalar multiplication is not a valid operation on S because, for example, the vector 1, 1 belongs to the open first quadrant, but when we multiply it by -1, this is now in the third quadrant. So here's the story, this theorem, and its proof is really nothing more than applying the definition of a valid binary operation. Let S be a non-empty subset of a vector space V. The restriction of addition on V to the subset S is a valid operation on S if and only if S is closed under addition, which means that if you take two vectors in S, their sum must also be in S. That's closure under addition. Notice here that we're not talking, when the term closure applies to S, not to the operation. I've heard students say addition is closed. That makes no sense. It's the subset S that's closed under addition. The restriction of scalar multiplication on V to the subset S is a valid hybrid operation if and only if S is closed under scalar multiplication. So we take a vector in S and a scalar. The scalar multiple is again in S. Also, a subset S is closed under both addition and scalar multiplication if and only if S is closed under linear combinations. So that looks like this if I fix it. Now, when both addition and scalar multiplication are valid operations on S, in other words, when S is closed under both operations or under linear combinations, then S is actually a vector space in its own right under those restricted operations. So here's the theorem. Again, S is a non-empty subset of V, and the following are equivalent. S is closed under the addition and scalar multiplication of V. That's equivalent to saying that S is a vector space in its own right under the restricted operations. And then we say that S is a subspace of V. And this is the notation that I use. It's very common. S, this is the less than or equal to sign, but this would be read S is a subspace of V. The key observation in the proof is that associativity and commutivity of addition and the properties of scalar multiplication hold automatically in the subset S. We're just simply restricting two vectors in S. It's not going to violate any of the laws that we already had in V. If addition is associative for all vectors in V, it's still associative for the vectors in S. There's nothing to check. The only thing that remains to check is that S is closed under negatives and that the additive inverse of V belongs to S. And that completes the demonstration that S has all the properties of a vector space. As far as closure under negatives, that follows immediately from closure under scalar multiplication, because the negative of a vector is equal to -1 times the vector. This is in S, therefore so is this. And as far as the fact that 0 must belong to S, well, if you take any vector in S, call it V, we already know that -V is in S, and so the sum is in S because S is closed under addition. The sum is 0. So that takes care of it. Okay. I might mention that the definition of subspace, there are two common definitions. One is that a subset is a subspace if it is a vector space in its own right under the restricted operations. So that is part 2 here. S is a vector space in its own right under the operations of V restricted to S. Some authors use that as the definition of subspace. Some authors use the first line here as the definition of subspace. S is closed under addition and scalar multiplication. I take exception to that definition because it's not in the spirit of abstract algebra. Substructures are subsets of any algebraic structure that inherit the structure from their parent. Subgroups of a group, subrings of a ring, subfields of a field. A subset of a group is a subgroup because it's also a group under the restricted operations. Same thing for subrings, subfields, subspaces, submodules, sublattices. I think that's really the essence of what's going on. It's a theorem that a subset S of V is a subspace if and only if it's closed under the two operations. So there's a distinction between the definition of subspace and the theorem that characterizes subspaces in a more practical way. But to avoid any controversy, to avoid the difference in definitions, I simply said that these two statements are equivalent, and if either one holds, we have a subspace. So I didn't split that hair, even though perhaps I should have. Okay. Let's look at some examples of subspaces. The trivial subspace is the subspace of any vector space just containing the zero vector. Okay. Another subspace, every vector space V has a trivial subspace. For every vector space V, V itself is a subspace of V. Okay. If V is a vector space and if little v is any vector in V, then the set of all scalar multiples of little v is a subspace of V. It's closed under the two operations, making it a subspace. It's called the subspace generated by or spanned by little v. One sometimes sees it written this way, and maybe I should add that to the notes. It looks a little funny, but what this means is just simply the set of all scalar multiples of V. We can generalize this. If X is any non-empty subset of V, then the set of all linear combinations of vectors in X is a subspace of V because it's closed under linear combinations. You take a linear combination of linear combinations, you just get one great big linear combination. This is called the subspace generated by X or spanned by X. And there are two notations we will use. Angle brackets around X, which is convenient and simple, or sometimes, for a little more emphasis, span of X. Incidentally, if you recall our discussion of linear combinations and context, in this context, of course, the linear combinations are being evaluated as vectors, so they're thought of as vectors. No other interpretation would make sense. The interpretation of these linear combinations as formal expressions wouldn't fit this description. We'll come back to this later. This is a very important example. It's well known that the subspaces of R2 are of three types. Speaking in geometric terms, the origin, in other words, the trivial subspace, any line through the origin, and also R2 itself. A line in R2 that doesn't go through the origin cannot possibly be a subspace because it doesn't contain the zero vector. And it's not going to be closed under addition. For R3, you probably also know the subspaces are the origin, lines through the origin, planes through the origin, and all of R3. The set C sub 0 of F of all infinite sequences with elements in F that converge to 0 is a subspace of the full sequence space. This is sort of an elegant way of saying that the sum and scalar multiple of sequences that converge to 0 also converge to 0. Notice that if we didn't use 0, if we said consider the set of all sequences that converge to 1, this would not be a subspace because it's not closed under either scalar multiplication or addition. If If you have two sequences that converge to 1, their sum converges to 2. The set S of all polynomials over F that are even functions. That means that P of negative x equals P of x. That's a subspace of F square bracket x. The set of all upper triangular n by n matrices is a subspace of the full vector space of all n by n matrices. Also, the diagonal matrices form a subspace. The set of non-singular n by n matrices is not a subspace of the full vector space, because the sum of non-singular matrices does not have to be non-singular. Neither does scalar multiple. If you multiply by 0, you have a problem. Or put another way, the 0 matrix is not in this subset. So there's all sorts of reasons that fails to be a subspace. Here's an example you probably have never seen. Consider this vector space Vn comma 2. This is the vector space of all binary n-tuples. N-tuples whose components are either 0 or 1. In other words, n-tuples over the field Z2 of an earlier example. Addition and scalar multiplication are performed modulo 2. And this vector space is very important in a branch of mathematics known as coding theory. It's the study of error-correcting codes. The weight, which I denoted by script W, of a vector V is the number of non-zero, I think the word component is correct, components in V. So for instance, here's a word of length, 7, and it has 3 non-zero components, so the weight is 3. It's the number of ones. The set En of even weight vectors is a subspace of Vn2. Of course, that has to be proved. One has to show that the sum of two even weight vectors has even weight. And to do that, we use this formula. This notation, U intersect V, is by definition the vector whose ith component is the product of the ith components in the two vectors. And remember, product means product mod 2. So I'm going to let you ponder this formula and why it's true. But it does follow that if the weight of U and the weight of V are even, then because we're adding these two together and subtracting twice some other number, this will be even as well. As to scalar multiplication, the only two scalars are 0 and 1, so scalar multiplication is pretty trivial. If you multiply by 0, you get the 0 vector, which has even weight. And if you multiply by 1, you don't change the vector, so if it had even weight to start with, it still has even weight. So this is the even weight subspace of Vn2. One last thing on subspaces, individual subspaces. Since all subspaces of a vector space V contain the 0 vector, it's not possible for two subspaces to be disjoint. disjointness never occurs among subspaces. They all have one vector in common, at least the zero vector. So it's a kind of a waste of term, disjoint. But the next best thing is when two subspaces intersect only in the zero vector. They only have the zero vector in common. And that does occur quite often. We will need to refer to that quite often in the course. So it seemed like a good idea to give that a name. This is not standard terminology, unfortunately. Maybe someday it will be. We say that two subspaces S and T of a vector space V are essentially disjoint if their intersection is trivial. In other words, the intersection is the trivial subspace. If V is a vector space, then the family, which I'm denoting by sub V, of all subspaces of V is actually quite an important gadget. As a matter of fact, it has two different algebraic structures, an additive structure and an order structure. So let's look at the additive structure first. If we have two subspaces, S and T, of V, then we can define the sum of the two subspaces pretty much as you would expect. S plus T is the set of all sums. U is in S and V is in T. U plus V. U is in S, V is in T. Note also that this is the same as this, which is the set of all sums U plus V, where U and V belong to the union of S and T. And I'm going to let you ponder why these two sets are the same. This sum of subspaces extends pretty easily to finite non-empty families of subspaces, and also, well, almost as easily to arbitrary non-empty families of subspaces. So here's the definition again for two subspaces, the sum S plus T. If we have a finite family of subspaces, then the sum can be written S1 plus dot 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 plus Sn, but also using the sigma notation, it can be written this way, and that is the set of vectors that are the sum of vectors from the different subspaces in the family. And that's also the same as the sum of the vectors u1 through un, where uk belongs to the union of the family. Basically, it's just all possible sums you can form from vectors anywhere in the family. And finally, if we have an arbitrary family that looks like this, then the sum, you can't take infinite sums in a vector space, at least not in general vector spaces. And so the sum of an infinite family has to be finite sums of vectors that come from the family members, or that, in other words, belong to the union of the family members. So here's a couple of quick examples. In R4, which is the set of four tuples, as you know, of real numbers, this subset has arbitrary first and second components. The other two components are 0. And this subset, subspace, contains the ordered four tuples where the second and third components are arbitrary. First and fourth are 0. So all you have to do is figure out what the sums look like. The sum of a vector in S plus a vector in T. So it looks like X, Y plus Z, W, 0. But since Y and Z range over all real numbers, Y plus Z simply ranges over all real numbers. And so we can write this more compactly as the set of four tuples X, U, W, 0, where X, U, and W range over the real numbers. Okay. Another example, let L0 be the subspace of the space of n by n matrices over a field, consisting of the lower triangular matrices, but with zeros on the main diagonal. So one might say strictly lower triangular. Zeros on the main diagonal as well as above the main diagonal. And U0 is the subspace consisting of the strictly upper triangular matrices. So zeros on the main diagonal, zeros below the main diagonal. Then the sum is the set of all matrices that have zeros on the main diagonal. It can be anything else, everywhere else. It's, you might say, the complement of the diagonal matrices, except for the zero matrix, that's included as well. It's not very hard to show that the sum of a family of subspaces is closed under addition and scalar multiplication, and so it's a subspace. And I will let you write a formal proof of that if you wish to. Addition of subspaces actually has some rather nice algebraic properties. It's associative and it's commutative because, after all you're doing is adding vectors, in this case from S, T, and U, and since ordinary vector addition is associative, that carries over to addition of subsets, or subspaces, sorry. Same thing for commutativity. The trivial subspace is the zero element of this addition, because when you add 0 to all the vectors in S, you just get S. Unfortunately, however, well, it's just the way it is, fortunate or not. I guess that's a value judgment I shouldn't make. In any case, no non-trivial subspace has an additive inverse. You can't take S and add it to another subspace and annihilate everything except the zero vector. It doesn't work that way. If you tried to take negative S, that's the set of negatives of all the vectors in S, you just get S back. So that then you'd have S plus S, which is not zero, not the trivial space. So sub V is a commutative monoid. Remember, monoid requires a single binary operation that's associative and has an identity. And we have just shown that that is the case here. And it's a commutative monoid because we have commutativity of addition. But it's not a group. because we're missing, it's not an abelian group because we're missing negatives. We're missing additive inverses. Again, when you try to add S and negative S, you just get S. You don't get the trivial space. We're going to see that the additive structure on sub V is actually quite important because it tells us how to take the join of subspaces in this lattice. Remember, sub V is the subspace lattice, a complete lattice. Meet is intersection. Join is more complicated, but we can use, in fact, the sum to give us some real insight into the join within this lattice. Okay, let's take a look at the order structure of sub V. And again, I remind you that if you did not study Appendix B, or if you did not watch my lecture on partially ordered sets and lattices, now would be a good time to do that. The family sub V is partially ordered by set inclusion, because the subspaces are just subsets of V. The trivial space is the smallest or minimum element in this subspace lattice, and the entire space V is the maximum element in the lattice. Moreover, sub V is an intersection structure, which we'll prove in a minute, and therefore a complete lattice. We had actually shown that, or discussed that anyway, in Appendix B and in an earlier video. I drew a picture here to help in case some of these ideas are a little abstract for you. This is a vector space V, and I have a family of 4 subspaces, S1, S2, S3, and S4. Meet is intersection, so I made the intersection a bit darker. It's the intersection of these 4 subspaces. Join, as you know, is the intersection of all of the upper bounds for this family of 4 subspaces. And so I drew dashed ellipses here. How many? 3? Yeah. And so I'm assuming, it's not the case, but I'm assuming that there are only 3 upper bounds for these 4 subspaces. Okay. V itself is an upper bound as well. So to get the join of these 4 subspaces, by definition, that's the smallest subspace containing S1 through S4. I take all the upper bounds, in other words, all the subspaces that do contain these 4, and I intersect them. And that's the big shaded region. That is the smallest subspace containing these 4 subspaces. So it is the join. Here's the proof that this family is an intersection structure. If you take 2 vectors from the intersection of the family, then those 2 vectors belong to each member of the family. That's what the intersection means. Therefore, any linear combination of the 2 vectors belongs to each member of the family, because this is a family of subspaces, not just subsets. And since an arbitrary linear combination belongs to every family member, it belongs to the intersection. So the intersection is closed under linear combinations. This holds also, by the way, for the empty family, because the intersection of the empty family of subspaces is the whole space V. And so, of course, it's closed under linear combinations. So sub V is, in fact, an intersection structure. Therefore, by the information in Appendix B or in our earlier lecture, we can, if we have a family of subspaces of V, the intersection is the meet, or maybe I should say it the other way, the meet of the family is the intersection, and the join of the family is the intersection of all upper bounds for the family. Now this description of the join is not altogether satisfactory, as I mentioned when we talked about this earlier, in an earlier lecture, because it doesn't give us any insight as to what the elements, what the vectors in the join look like. Not to worry. The join is the same, is equal to the sum of the family members, and we know what those vectors look like. They are just finite sums of vectors from the union of the family. Why is this true? Well, we need to show that the sum has the defining properties of the join, that it is a subspace of V, that it contains every family member, and that it's the smallest subspace of V that contains every family member. We already know it's a subspace, but since the sum of a family of subspaces is the set of all finite sums of vectors from the subspaces, that includes one-term sums, the simplest sum of possible. So if S is in the family of subspaces, then S is also in the sum of the family. So every subspace in the family belongs to the sum. The sum contains every member of the family. All we have to do is show that it's the smallest subspace that contains every member of the family. Well, if we take a subspace W of V, it is that contains every member of the family. It's closed under sums because it's a subspace. So if W does contain every member of F, it contains all the sums of vectors from the family, or from the union of F if you prefer. So the sum of the family is contained in every subspace. Therefore, it's the smallest subspace that contains the members of the family. So in summary then, if V is a vector space, the subspace family, sub V, is an intersection structure closed under intersections. In other words, the intersection of any number of subspaces is again a subspace, and therefore it's a complete lattice. Meet is intersection. join in this case, in the case of vector spaces, is the sum of the family, the set of all finite sums of vectors from anywhere in the family. In other words, any subspace in the family. So that's why we call it the subspace lattice. I think I used that term prematurely a little earlier, but actually maybe I discussed it in that previous lecture on lattices, so it may be okay. Sometimes I can't remember whether I've discussed something or not after several lectures go by, so you'll forgive me if I misspeak. Here's an example, again in R4. Remember these two subspaces. We took their sum earlier. The meet is the intersection, so we have to ask ourselves which ordered four tuples satisfy both of these conditions, and the answer is you've got to have 0 in the first component, in the third component, and in the fourth component. So the second component is the only one that can range over the real numbers. And the join, as we saw before, is the sum. So this is, in fact, the smallest subspace containing both S and T. It is not the union. Here's another example. Again, we have the L0, the subspace consisting of strictly lower triangular matrices, and U0, their meet is their intersection, and that is only 0. Only the 0 matrix survives both requirements. 0 strictly below the main diagonal, and 0's on. I'm sorry, let me say it again. The only non-zero elements are strictly below the main diagonal, intersected with matrices that have non-zero entries only above the main diagonal. You can't have it both ways unless the matrix is 0. And the join is the sum. And I'm going to let you think about what the sum is. Well, actually, I said what it is, but I'm not going to repeat this now. I mentioned in the earlier lecture that it's tempting, perhaps, at first glance to think that since the meet is intersection, maybe the join is the union. But I also mentioned that the union of subspaces of a vector space is almost never a subspace. The only time it's a subspace is when one of the family members contains all the others. So the union is the largest subspace, and therefore it's a subspace. Any other time, the union of subspaces fails to be a subspace. This is an interesting property that I have never seen in any other undergraduate linear algebra book. Of course, I haven't seen all the books, so it might be somewhere. But anyway, let's take a look at the theorem. V is a vector space. Now this must be an infinite field. So vector spaces over finite fields are a different story. But this would include the real vector spaces and the complex vector spaces, which are in many respects the most important ones. We have a finite family of subspaces. Then their union, which I'll just call U, is a subspace of V if and only if one of the subspaces, say SK, contains all of the other subspaces in the family, in which case the union is just SK. So let's look at the proof. It's a tiny bit clever. Of course, if one subspace SK contains all the others, as I've just got through saying, then the union is that subspace. So it's the converse that really presents any difficulties. So suppose the union is a subspace, but that no member of the family contains all the other members. We'd like a contradiction. Well, we can examine all the subfamilies of F. F is a family of subspaces. Look at all the subsets of F, which we call subfamilies. To find one with the fewest number of subspaces whose union is still equal to the full union, U. In other words, there's only a finite number of subspaces in the family. We can look at we can throw away some. We can look at all the subfamilies, look at all their unions, find the one with the fewest number of subspaces whose union is still U. This minimal subfamily has the property that no member of the subfamily is contained in the union of the other members. In other words, every surviving member of the subfamily contributes something to the union. If it didn't, we could toss it out and get yet a smaller subfamily with the same union. So everything contributes in this minimal subfamily, or it wouldn't be minimal. Now, rather than re-index and make life more complicated, we can just go ahead and assume that the family F itself has this property. We can't yank out anything and get the same union as before. Everything contributes a unique vector to the union. So S1 then is not contained in the union of S2 through Sn, or we could toss it out and the union would not have changed. Similarly, S1 does not contain all the other family members. That's something we've already assumed is not the case. So we can select a vector that lies in S1, but that's not in any of the other subspaces, S2 through Sn. So it's not in their union. And we can choose a vector, U, that is in the union of S1 through S2 through Sn, but not in S1. Now we look at these linear combinations of U and S1. U plus A S1, where A ranges over the field. This is an infinite set because of our assumption that F is an infinite field. These are all distinct, and I'll let you ponder that. Note also that no member of this set, no vector of this form, belongs to S1, because if U plus AS1, little s1, belong to big S1, then we could subtract a S1 from it, little s1 belongs to big S1, and this difference would also belong to big S1, but the difference is u, and u does not belong to to big S1. Okay. So no member of this set, no vector in this set belongs to S1. Remember, we're looking for a contradiction, just to remind you. Moreover, since A is infinite, but the family of subsets is a finite family, one of the subspaces, and it must be S2 through Sn, because of what we just showed, must contain at least two members of this set A. In fact, infinitely many. So we have this infinite set of vectors. They all belong to one of these family members, S1 through Sn. None of them are in S1, therefore they're all in the other family members, S2 through Sn. There are infinitely many of them. There's only n minus 1 subspaces. One subspace must contain at least two, in fact, infinitely many of the vectors in A. I only need two. I don't need more than two. So let's say these are the two, u plus AS1 and u plus BS1. And let's say they belong to SK. K is bigger than or equal to 2. What happens when we subtract these two? Still belongs to SK, but the u's cancel, and we have the quantity A minus B S1. A minus B is non-zero because A and B are different. That's the whole point. We needed two distinct vectors of this form belonging to one of the family members. I don't care which one. But the difference here, A minus BS1, would therefore also lie in SK, and that is a contradiction because S1 does not lie in any of these vectors, doesn't lie in subspaces, it doesn't lie in SK. So that's the contradiction. So U, in fact, cannot be a subspace of V. We should note that, in general, the theorem we just proved about the union of subspaces does not hold, in general, for vector spaces over a finite field. And I'm going to leave it to you to provide an example. So we have shown then that the union of any finite family of subspaces of a vector space over an infinite field is a subspace only in the most obvious, or you might say trivial cases, where one subspace in the family contains all the other subspaces. And so the union is just the largest subspace. As to infinite families of subspaces, the situation is more complex. Just to give you an example, in R3, the union of the family of lines through the origin that are contained in the xy plane is the xy plane. And so it's a subspace of R3. But if we enlarge that family of lines by tossing in, say, the z-axis, the union now is no longer a subspace. So for infinite families, the union might be a subspace, it might not be. But there is a case where the union of an infinite family of subspaces is a subspace, and this is important enough to deserve some special attention because we will use it later. A chain C in a subspace lattice sub V is a totally ordered subset of V, of sub V. This is something we discussed when we talked about partially ordered sets. A chain in any partially ordered set is simply a totally ordered subset. So in the case of the subspace lattice, it looks like this. If you make two subspaces in the chain, then let's say S and T, then either S is contained in T or T is contained in S. An example of a chain, say in the polynomial space, f square bracket x, is the subspace generated by 1. That's contained in the subspace generated by 1x, which is contained in the subspace generated by 1x, x squared, and so on. This is a chain in the subspace lattice for f square bracket x, because given any two of these, one is pretty obviously contained in the other. But it's really important to understand that not all chains are infinite sequences. This example is an infinite sequence of subspaces. Each one contains the previous one. Here's an example of a chain in a subspace lattice that is uncountable, so it's not an infinite sequence. Let this notation, if you recall, Q superscript R, stands for the family of all functions from R to Q, from the real numbers to the rational numbers. And we had an example earlier that showed that as long as the codomain is a vector space, this family of functions is a vector space. And Q is a vector space over itself. And so this family is a vector space over Q. And you can check that more carefully if you want by looking at the definition of vector space. Now, as shown in this figure, we'll set for each real number R, let S sub R be the set of all functions from R to Q for which f of x is 0 for x bigger than or equal to R. So I just drew some graphs of functions here. Once we reach R, the graph is flat, 0. So all these functions, and these form a subspace of Q to the R. If you add two of these, since from R on it's 0 for both functions, the sum also has that property. If you scalar multiply one of these, you'll get another one. So these are subspaces. And I have now a family of subspaces indexed by the real numbers, little r. So this is an uncountable family of subspaces. Okay. I probably should mention that explicitly. Now, if we take two real numbers, a and b, a less than b, then the subspace S sub a is the set of all functions that are 0 from a onward, and S sub b is the set of all functions that are 0 from b onward. Well, if we have a function that is 0, let's say a was 1 and b was 2. If we have a function that's 0 for all x bigger than or equal to 1, it's certainly 0 for all x bigger than or equal to 2. So S sub A is contained in S sub B. And therefore this family is an uncountable chain of subspaces. I didn't need to add that, I already did. Okay. So you can't write this family as an infinite sequence the way we wrote this family. It's like trying to write the real numbers as an infinite sequence, and we know that's not possible. So that's the story on chains, and it's important to remember the distinction between a chain and an infinite sequence that's ordered. Chains are more general. The union of any chain of subspaces of a vector space will always be a subspace. That's the theorem here. V is a vector space. Here's a chain of subspaces. The union is a subspace, and here is the reason. All we need to do is show that this union is closed under linear combinations. So if we take two vectors u and v in the union, then u is in one of the family members, say t sub I, v is in one of the family members, t sub j, but, and this is the key point, because C is a chain, one of t sub I and t sub j is contained in the other. And we can assume by reindexing or by symmetry that t sub I is contained in t sub j. That means that both of these vectors, u and v, lie in the bigger subspace t sub j, and so any linear combination of u and v will also lie in t sub j and therefore be in the union. So the union is closed under linear combinations and is therefore a subspace of V. It might be worth pointing out a subtlety here that's actually quite fascinating. The reason this worked is not just because C is a chain of subspaces, but because linear combinations involve only a finite number of vectors by definition. We're dealing here with just linear combinations of two vectors. If we had to show closure under infinite linear combinations, whatever that might mean, it's meaningless, but let's just pretend for a minute that you could take infinite linear combinations. This would break down. This proof would break down. Even if C is a chain, it wouldn't work. So the reason that this works is because linear combinations, by definition, involve only a finite number of terms, or a finite number of vectors. So there is a finiteness about, well, linear algebra, about linear combinations in particular, that makes this work. In the setting of analysis, where you do deal with infinite sums that converge, the flavor is quite different. You don't have this finiteness flavor that you do in algebra, in abstract algebra. This is one of the things that distinguishes the flavor of algebra from the flavor of analysis. They have quite a different feeling because algebra has this finiteness property. Binary relations, just input has size 2, and of course unary and nullary relations even smaller. But we talked about this briefly before, but in analysis you deal with infinite sequences and limits. It's just a whole different feeling.